Hello again. I'm back with another lecture about Boolean unsatisfiability. So you recall from the previous lecture that we're looking at sat solving, pure, simple propositional logic. And in particular, we're interested in the case where the formula is unsatisfiable, and we want to be able to generate a checkable proof that that's the case. So what I'll talk about today is how standard so-called CDCL solvers work and how they are naturally able to generate proofs in something that's a variant or an alternate way of describing resolution. So recall from last time that we had this example Boolean formula consisting of 6 clauses, and we can write that in a standard file format called the DIMACS file format, where we use positive integers for variables and negative integers for their complements. And we list a clause as just a series of literals, or positive and negative integers, terminated by 0. And I showed before that we can use resolution to take those clauses and systematically derive the empty clause from it. And since each of those resolution steps is an implication step, it shows that the input formula implies false and therefore is not satisfiable. But we're sort of left with the question of, yeah, well, okay, you can draw me a proof for this example, but how could I actually derive that? In particular, how could a SAT solver derive that automatically? So let's look a little inside of CDCL, conflict-driven cause learning solvers, and how they operate. So a core trick that all SAT solvers use is known as unit propagation. And it's taking advantage of the fact that if a clause contains just a single literal, then we must set that literal to something true. So in particular, if the clause has a single variable x, then x must be assigned value 1. And similarly, if it contains the x bar, the complement of x, then it must be assigned 0. So that's so-called unit clause. And now once we've assigned x or a literal to 0, meaning we falsified that particular literal, then if any clause that contains that literal, we can just take it out because it's not going to be set to true, it's set to false. And so it can't help make that clause be satisfied. On the other hand, if we have a clause that contains the literal that we've just assigned 1, then that clause is satisfied and we no longer need to use it. So this example at the bottom shows a simple example of unit propagation. You'll see that we have 4 clauses, but the rightmost one is simply the clause C. And so by unit propagation, by the unit rule, C must be assigned 1. And so I'll show that here in red. And that means that these last 2 clauses will be satisfied. But these 2 clauses containing C bar, now I can remove that. Or I'll show it here by turning them into dark or light gray, saying that C bar isn't going to help you at all in satisfying these clauses. But now you'll see that the leftmost clause becomes unit. The only remaining literal is A. And so we must, by the unit rule, assign A to be equal to 1. And we can now do unit propagation. It will say that this clause now becomes satisfied. And the second clause, we have A is assigned 1 and C is assigned 1, so those won't help. So now we have a unit clause here containing B bar, and therefore we must set B to 0. And the result of this is you'll see that the entire formula, we found an assignment, A equal 1, B equals 0, and C equals 1, that will satisfy these clauses, and in fact it will uniquely satisfy these clauses. So unit propagation is a pretty useful trick that we want to apply in part of our searching for a solution. So this pseudocode shows the overall structure of a CDCL solver. And as I mentioned, CDCL stands for conflict-driven cause learning. The point of which is that the key components of it are trying to search for a solution but detecting cases where our search is coming up with a conflict, an impossible combination of variable assignments. And from that, we want to learn from our mistake and be able to then make sure we never repeat that same mistake again. That dead end, it's not really a mistake. So the overall code is a nested loop. And you can think of this as a fairly standard type of search, except that it's exploiting unit propagation as much as we can. So let's look at this inner loop. And you can see what it's doing in the loop is choosing some variable and assigning it either 0 or 1. So it's sort of classic search. But we also always attempt unit propagation whenever we can. And you'll see that it's not apparently systematic. It's not sort of clearly saying in what order to assign variables or what values to assign them. We'll sort of let this cause learning part of it drive what direction things go. So we'll make use of unit propagation, whatever information we can garner from the formula as we go. And then if we're at some point where we've satisfied all the causes, then we've created a unique solution, or a possible solution. It might not be unique. On the other hand, if we've detected some conflict, meaning we've attempted to assign opposite values to a single variable, then we've hit a dead end in the search, and we can generate what's known as a conflict cause, meaning a cause that says, I've searched and tried to assign the following variables, and that didn't work. So at least one of those variables I want to assign the opposite value. And that's what a conflict cause is. It's saying, I'm sure that the satisfiable solutions must satisfy this particular set of constraints. And then we'll go back through the loop and we'll unit propagate with that so-called learned cause. And we'll keep doing this until we either hit a solution or we hit a conflict. You'll see that the conflict case also, it causes us to break out of that inner loop. And if we've broken out of that inner loop in a way that we haven't assigned a single variable by choice, it's all been forced by unit propagation, then we can definitely say this formula is not satisfiable. On the other hand, if we've at least one of these, we've made at least one of these choices, then we have to keep going with our search. So let me illustrate this with an example using our example formula. And so at first we look at this formula and we say, are there any unit causes? And the answer is no. So no unit propagation is possible. So let's choose some variable. In this case, let me choose variable b. And let me just assign it 0. So that's what this blue line, think of it as an evolving search tree. And what I've said is, I'm going to try setting b to be 0, b to be false. And right away, in doing that, I'll get unit propagation on both clauses 5 and 6, one of which will set d bar, and the other which will set d. So that's a conflict, and I've reached this position. And what this tells me is, any assignment to this formula that tries to set b to 0 is going to lead to a conflict. And therefore, I can assume that b has to be 1. And so I'll add a unit clause that I've learned, which is basically to take all the variables that I've made choices on along the path and complement them and produce a clause. So in general, it won't be a unit clause, but in this particular case, it is. Now let's go back again. I go back to the top of my loop and I start a new case of the inner loop. And now I can do unit propagation on b bar. So you see it's expanding my search tree just by the existence of this conflict clause that I've learned. I have to assign b to be 0. And when I do that, I don't get any further unit propagations. So let's pick variable c and let's just try assigning it value 0. Well, again, I get a propagation here because I've assigned b to be 1 and C to be 1. And so this first clause will cause a unit propagation of A bar. And A bar will cause another unit propagation on clauses 3 and 4. I'm trying to assign it both D bar and D, so another conflict. And so now I can, again, do a learn clause. In this case, it says any assignment that assigns value 1 to C is going to lead to a conflict. And therefore, I can add the clause C bar. Now I go back through a third iteration of my outer loop. And you'll see that I can make use of my unit propagations B and C bar. And that will right away force the second clause to have a unit propagation of A bar, which gets back to my conflict in clauses 3 and 4. So that will immediately give me a conflict. And you can see then I've made my way through with all pure unit propagations through this augmented formula and gotten a conflict. And therefore, I can reliably say that this formula is unsatisfiable. So that's how CDCL works. Now, you look at that tree expansion that shows the search history and the implications that were made out of that. And if you flip that tree 180 degrees rotated, you'll see, lo and behold, you get our resolution proof. And that's not an accident. It's logically, you can see that the kind of inferences we're making through unit propagation are exactly the kinds of inferences that provide for resolution steps. So let's look a little bit deeper, and we're going to take the idea of resolution, but come up with a more algorithmic way to apply it, actually a sequence of resolutions, a linear sequence of resolutions, and potentially a subsumption step. And that's a technique known as reverse unit propagation, or it's just called RUP. And RUP is the sort of core step that we'll have in our proofs, that each step in our proof of unsatisfiability will be a new clause that we've introduced, and it will be according to one that follows by one RUP step, one reverse unit propagation step, applied to the preceding clauses. And the idea of a RUP step is we're given some set of we have some clause that we want to add to our proof. It's going to be a conflict clause, a learned clause. And we want to be able to show that that new clause follows from the previous set of clauses that we've already have in either the original formula or that we've added to the proof as we've been going along. So call those clauses D1 through DK. There will be some subset of the clauses, again, both the formula and the proof up to this point. And the strategy then is we'll do it by proving a conflict, proof by contradiction. In other words, we want to prove that the conjunction of all the D's implies C, but the way we'll do that is we'll assume the negation of the consequent. We'll assume that C is false, and show that that leads to conflict, a contradiction with the existing clauses. So in particular, think of clause C that we're trying to add is a series of M literals, and we have K previous clauses. So what we'll do is we'll form the negation of C, and the negation of the clause then is actually a sequence of linear of unit clauses. It's a conjunction, each of which is just a single unit clause, formed by complementing each of the literals in the original formula. So if, let's say we assume that's the case, and then we want to show there's a contradiction of that with these so-called antecedent clauses, the ones that are sort of providing the supporting foundation for this, the proof of this step. And we'll order these and make sure this works in such a way that each subsequent clause in here will add one more unit clause to the list of units that we've learned so far, beyond those that were formed from negation of C. And then the final clause, D sub k, will have a contradiction that says that all of its literals will be unsatisfied by these set of units, and therefore this implication, this contradicted implication is false, and therefore the original implication is true. So let's show this by example. And this will show you, in fact, how the search that we did using CDCL will turn very directly into a RUP proof. So you recall that the first literal we learned, the first clause we learned, was B. B has to be hold in this. And so let's see if we can use a RUP step to prove that's the case. And so the way I've written it here is on the left is what we're trying to prove, and on the right are the antecedent clauses that we're going to use to prove it. And up above in red are the unit clauses that we've learned along the way. So we'll take the negation of B, which is simply B bar, and we'll check out clause 5, and it says B or D bar. Well, if B is false, then we have a unit propagation of D bar here. And now, if I compare that with the final clause, D, I have both B bar and D bar, so both of these literals are falsified, and that's a conflict. So this shows that we can add this clause, this unit clause, to the series of clauses by the RIP rule, meaning that it's logically implied by the preceding clauses. And similarly, we can add the clause C bar, and you'll see that one of its antecedents is the clause C7, the clause B. So we get to use as antecedents either the input formula clauses or any of the previous clauses that we've added to the proof. And you can step through it, and you'll see again by a sequence of unit propagations will derive a conflict. And the final step is we have an empty clause, and that's because by a sequence of unit propagations starting from an empty set, we'll get a conflict with clause C4. And so you'll recall those were exactly the three different passes we made of that inner loop in the CDCL solver, and you see it arrived at this empty clause as a proof, and that shows then that through these three RIP steps, we've given a proof of unsatisfiability for the formula. So each RUP step, remember, is really just a series of resolutions. So it's all based on the resolution principle and possibly subsumption. And so that's a proof. And in fact, the standard way that CDCL solvers produce their proofs, the files, is called DRAT. And we don't have to talk about what DRAT stands for. But RUP is one of the proof rules allowed by DRAT. And all we have to do, all the sat solver has to do is produce, it doesn't even have to produce the antecedents. It just has to list the clauses, starting with the clause for B, which is 2, the clause for C bar, which is -3, and then the empty clause. You'll remember we use the 0 as the terminator for a clause, so just the line with the 0 is the empty clause. And that is, in fact, a proof that a CDCL solver could generate and would be a checkable proof of the result. There's another tool that we'll describe that takes a DRAT proof, and its job is to add the antecedents. So it has a very simple polynomial time search algorithm that lets it scan, given a target clause, lets it find among the preceding clauses a set of antecedents that by the RUP rule will imply that target clause. And the final format that it turns into is one called LRAT, which is the lowest level format where the proof has to be fully annotated with the antecedent clauses. So you'll see I've numbered the clauses here, C5 and 6. I just say 5 and 6. And so a line in LRAT has both a clause terminated by 0, and then the series of previous clause numbers indicating what steps to use this RUP checking for. And they have to be done in a particular sequence so that that one pass through it can be done. Again, the list of these clause identifiers then is terminated by 0. And so the proof infrastructure for this is a pair of programs called DRAT trim followed by an LRAT checker. So DRAT trim's job is to take the output of the SAT solver, which is just this list of RUP clauses, and annotate it with the antecedents so that it's in this low-level form that can be checked step by step, just making sure that each step obeys the RUP property and a few other general properties as well, but something that can be easily checked. And that will become my check of the result. So you can think of DRAT trim's job is to take a sort of skeleton of a proof and solidify it into a real proof with antecedents. And then the job of the LRAT checker is just to make sure that each of those rules is obeyed. So there's, for the standard DRAT trim is written in C, and it may or may not have bugs in it. It probably does have bugs in it. So it's not a trustworthy tool, nor is the SAT solver a trustworthy tool, as I've said. But if we can trust the LRAT checker, then that's good enough. Because if there is some bug along the way, then that LRAT checker would be able to detect that something's wrong with this proof and say, nope, something is the matter here. And so the standard LRAT checker is one written in C, and it's designed to be fast and with high capacity. But there's also several formally verified LRAT checkers that have been written by different people in the theorem proving community based on different proof frameworks, ACL2, Koch, Hall. There's one now coming out in various other formats. And so if you have a formally verified checker, then again, even if the preceding programs are buggy, you'll be able to reliably say that this formula is unsatisfiable if it passes the LRAT check. So to kind of give you a perspective then, we've shown this very close tie between CDCL and resolution, that it's very natural every time you reach a conflict in CDCL that you generate a clause, and that can be checked with a RUP rule. And so the search through the possible search space of solutions very naturally is captured by the series of dead ends that are hit in this, and each of those turning into a clause. So that's the good news. It means that it's fairly straightforward to generate a proof from CDCL in this checkable format. The bad news is that means that if there's problems for which the resolution proofs are large inherently, that means that CDCL is going to do very poorly. An example of this would be the so-called pigeonhole principle, which is just the problem of saying, imagine I have n+1 pigeons, and I can assign each pigeon to a hole, and my rules are every pigeon has to be assigned to some hole, and no hole can contain more than one pigeon. So this is clearly an impossible combination. And it's fairly straightforward to encode this using a set of variables of the form p sub ij, saying that pigeon j is assigned to hole I. And I do this by n+1, at least one constraints, meaning every pigeon has to be in some hole, and n at most one constraints, meaning every hole can only contain at most one pigeon. And the total, because the at most one constraints are quadratic, will be cubic in n. So it's been was well believed and was rigorously proven back in 1985 that any resolution proof for the pigeonhole principle will be exponential in n. And that tells us that any proof that's generated using CDCL will also be of exponential size, and that's not good. Not that we particularly care about this problem, but it shows that there's this sort of problems that we can easily, from a high level, say this is clearly not satisfiable. But if we have to prove it using this particular proof framework, it's going to be very tedious and slow. Another benchmark that shows some weakness in CDCL solvers was shown as part of a paper by Chu and Höhle back in 2020. And it's an example of a class of formulas for which CDCL does particularly poorly. Imagine that we have two sets of parity constraints. One saying that the variables x1 through n have odd parity, and the other saying that they have even parity. So obviously, this can't be true. The conjunction cannot be true. To make it a little more interesting, let's assume that the second set of constraints, we've permuted the order of these by some random permutation. So it's not just totally transparent. And then we'll use our encoding trick that I already showed you to turn them into linear complexity. But you can think of one as doing a left to right evaluation of the parity constraints, and the other is doing it according to some random ordering of the variables. This is essentially a disaster for a CDCL solver. In particular, if you think about unit propagation on parity constraints, if there are k variables in that constraint at the high level, not including the encoding variables, then you only get unit propagation if you've assigned values to at least k minus 1 constraints. So unit propagation really only helps in this case when we've assigned values to all but one remaining variable. So the search is just going to go over and over again down, making choices, and only at the nth step learning anything, and each of the resulting clauses will be initially over n minus 1 variables and then slowly getting shorter. So really doesn't work. In fact, just to show you what I mean, this is an example of running KeySAT, which has been the winner of several SAT competitions. It's considered absolute state-of-the-art of CDCL solving. And because of the randomness in the permutation, KeySAT's runtime will vary from one permutation to the other. So for each size value of n that I tried here, I used 3 different seeds to get some history. And you'll see that my plot's on a log-log case chart. And you see I'm ambitious. I'm aspiring to be able to solve this problem, generate a proof, where n is up to 100,000. So I really, because this should be an easy problem. And I've also shown this on a log scale for time. I've limited the time to be 10 minutes, just for sake of making life simple. And it's log scale, so it tends to stretch things out. And in particular, on a log-log plot, if something is polynomial, it should be a straight line. And here you'll see the general trend is not straight. It's an upward curve, and that shows you that it's worse than polynomial. In particular, it's exponential. So you see here for this is up through fairly small values of n, it runs in well under a second. It does just fine. But now as I go from 20 up to 30, you see the times are starting to stretch out. And basically, once I hit n equals 42, I've hit the end where I can't solve these in less than 10 minutes, and in fact, they get much worse. And this is a typical phenomenon you'll see when a solver is hitting an exponential case, is it does great for the little cases. And then you just increment a little bit more and it starts to go into tens of seconds and hundreds of seconds. And you increment one more and it just will exceed any threshold that you set for it. Classic exponential case. So we see that for this problem that we can, again, at a high level, see this is clearly unsatisfiable. CDCL, or in general, to do it as a resolution proof, I don't think this has been proven as a hard lower bound, but there's similar ones over parity constraints for which there are lower bound proofs, that any resolution proof will be exponential in size. And that bodes poorly for CDCL. So that might say, oh no, we have to throw out resolution altogether if we're always going to be hitting exponential proofs. The good news is that by one little tiny tweak in resolution, we can come up with a much more powerful framework that's called extended resolution. And this is due to a Russian logician named Gregory Tsaitin, who did this work only 2 years after Robinson's work. And that's the origin of the name Tsaitin variable, by the way. And the idea of this is we'll do that same encoding trick you saw in turning formulas into CNF, of introducing new variables, but these new variables will be in the proof, not in the input formula. And they'll, just like we used for encoding the output of a logic gate or some sub-expression in a Boolean formula, we'll let this new variable encode some Boolean formula over previous input variables and previous extension variables. And we'll throw the clauses that encode that representation, z if and only if f, into the formula. They don't change the truth or falsity of the formula at all. But now in subsequent steps, I can reference that extension variable as in my new clauses that I'm adding to the proof. And if I can do that and still derive the empty clause, then it shows that the original formula is unsatisfiable. And this little idea is remarkably powerful. In fact, there are different proof frameworks, logical frameworks for propositional proofs, of which the weakest, one of the weakest is resolution. And extension resolution is as powerful as any known proof system for propositional logic. So that little change took it from a very weak system to a very strong system. So let's just show you an example, and this is very artificial because it won't actually help anything in my case. But imagine I wanted to encode A and B as a short, I wanted to introduce a variable z to represent that conjunction. And you can see why I might want to do it, because, for example, if I had z there, I could replace the A bar or B bar here with Z bar and turn this clause into Z bar or C bar, and this clause into Z bar or C. And you'll see that I've got A or D bar and B or D bar, and so I could, again, combine those two clauses to say Z or D bar. So it's not out of the question, this might be a good idea here. And so the way I'll do this is I'll introduce clauses that encode Z if and only if A and B, which, as we've already seen, can be done with 3 clauses. And now in my subsequent proof steps, I can reference variable Z and apply, again, the Rupp rule, potentially making use of the so-called defining clauses in my inferences, and again end up with a empty clause as my result. In this case, I didn't really save any clauses because, first of all, I had to add 3 clauses, and my inferences weren't any more compact. But you could imagine in other cases being able to abbreviate some complex combination of things over the clauses might actually be a good idea. So this leads to a possibility that if CDCL is intimately tied to resolution and it's bounded by that, but I've got this better proof technique, extended resolution. Is there some way I could adapt CDCL or some other SAT solving technique to generate extended resolution proofs and therefore overcome this? So for example, Cook, the same Cook who's the origin of P versus NP proof, the NP completeness theorem, showed way back when that he could generate a extended resolution proof that the pigeonhole problem is unsatisfiable with a quartic number of causes. Remember that the original formula is n cubed, so it's not that much worse to turn it into an extended resolution proof. So somehow there's a promise here that we could do better than what we're doing and generate short proofs. But various people have tried with CDCL to sort of learn extension variables and have generally failed. So this leaves open the possibility that there's some other approach to Boolean satisfiability that could make use of extended resolution and therefore get short proofs. But it's not going to be CDCL on its own. It's going to have to be something else. And that's what we'll look into as we go forward.